This video is going to talk about waves, particularly period, frequency, wavelength, and how those are related to the speed of a wave. So the first thing I want to talk about is if we imagine that we have a mass on a spring and we pull it down and it's going to bounce up and down, up and down, up and down. We can see that motion of a mass oscillating on a spring in this picture on the screen right now. So I could ask you to find the period of this oscillating mass up and down, up and down, up and down. The period is just the time required for this to make one complete cycle. So instead of picking it at like the middle, you'd want to pick at the top or the bottom. You can get out your timer and we can press go on our timer when the mass is at the top of its motion. So if we get ready, start our timer, goes down, and stop your timer. You should see that the time that it takes to go from the top to the bottom and back up again is about 6 seconds. That's going to be the period of this mass on a spring. Here I have a wave that is on a graph. If the y-axis of this graph is displacement, and the x-axis is time, then the period is the time it takes from the one crest to crest or peak to peak. This is the time. That is the period. You could also find the period from trough to trough, or you could do it, and I less recommended the period from when it crosses here. It'll go down, back to the middle, up, and back to the middle. So this is also the time or the period. So we use the letter T to represent the period, and that time is going to be the unit in seconds. Now, you might have seen this graph before. If instead of graphing time on this x-axis, I graph it as position, well, then peak to peak is no longer the period of this wave, but it is the wavelength. The length of the wave in meters or centimeters or nanometers, and we use the Greek letter lambda to represent wavelength, and the unit is some form of meters. Okay, so what happens if I decrease the wavelength, right? If I make this wave have a smaller wavelength. So I'm going to go ahead and draw that in maybe a hot pink. And no real difference in, like, not necessarily a half or a third, but just a smaller wavelength. Okay, so now I have that in hot pink here. So the wavelength has now decreased. You can see trough to trough, it's much smaller than the original black line. By decreasing the wavelength, I have now increased the frequency of this wave, or the number of waves that pass a point in a given time. So if I go back to this idea of time, here is time rather than wavelength, then you can imagine the amount of time that it's the number of times it oscillates up and down in a second will get bigger as the period decreases. So frequency and period are actually just inversely proportional to each other. So 1 over the period is the frequency of the wave. Okay, so this video, really the idea is we want to know, like, how fast is this going? Like, how fast is a wave, right? We could talk about how fast is the speed of sound, or we could talk about at what speed does light travel. And so in order to do that, we need to think about velocity is distance over time. But for a wave, that distance is just the wavelength, and the time is just the period. So I can write an equation that says the velocity of the wave equals the wavelength over the period. So that's the speed of my wave. Now, sometimes we don't really care about the period. When we have this mass oscillating back and forth, it's easy to think what the period is or to measure the period. But if this is sound, we don't really think about it as the period. We think about sound as frequency, like pitch. So something with a low frequency would be like this, and something with a high frequency would be like this. So we think frequency when we think about sound rather than period. So because frequency is 1 over the period, I can imagine that this is like 1 over the period here, and so I can just exchange that for frequency. So the velocity of the wave is just the wavelength times the frequency. So we typically think about light as having a constant speed, which is 3 times 10 to the 8th meters per second. That light would be anything in the electromagnetic spectrum, from radio waves to microwaves to X-rays to visible light travels at that speed. Now, that speed is technically in a vacuum, but the difference between the speed of light and air is so small that typically we take 3 times 10 to the 8th meters per second as being just the speed of light in general. But the medium that a wave travels through does affect its velocity. So the speed of sound in air is about 330 meters per second, while if we're talking about water, the speed of sound in water is actually faster. In this problem, 1,530 meters per second. You can think about why that might be and ask me later. So if I were to think about how to find the wavelength, what is the wavelength of sound in water? I have my equation. Velocity is the wavelength times the frequency. So velocity is wavelength times the frequency. So the speed of sound is 1,530 meters per second in seawater times the wavelength times the frequency of 2.5 times 10 to the 2 hertz. Now, Dr. P, that's written kind of weird. Yeah, that's in scientific notation, just to throw you off a little bit. This is actually 2.5. Move the decimal place over 2. So this number is actually 250 hertz. Now, if you remember, a hertz is just our unit for frequency. You could also say that as 1 over seconds. So that wavelength is going to be divide both sides by 250. And we get our answer of 6.12. Now we need to put a unit on that. It's sort of weird to cancel units out when we have hertz in here. So I'm going to go ahead and instead of using hertz, I'm going to write that in as 1 over seconds. So the seconds in the denominator up here cancel with this 1 over seconds here. So we're left with meters. So this would be this frequency 250 hertz is a pretty low frequency, or something that has a fairly long wavelength.